today we're here to talk to you about container security, like how you can secure your container workloads and why it's important to do so.
So before we talk about container security, let's go through what makes up a container. So everyone should be familiar, but just to set up the stage. So first of all, you need an OCI image bundle definition. So with OCI, we have standardized what makes up an image and how they are stored up in a registry. So basically, it's a tarball with JSON storing the configuration for the image. So once you have these images on a registry, what do you need to pull them down? So we created this library called containers image. And with this library, you're able to pull down images from any container registry that is compatible with Docker and OCI, and you're able to move your images onto your node. Then next, you get all these layers on your node, so you have to explode them into a copy out and write file system, so you get a root file system for your container. And for that, we have a library called container storage. Now, where did container storage come from? So Red Hat had been involved in Docker from the beginning, and we have contributed a bunch of drivers to that library. So this was extracted from the work we did there, basically getting all the drivers like overlay, device mapper, AUFS, Btrfs, and so on. So all of these drivers are supported in this library. And finally, you need a runtime to actually run your container. So the OCI runtime spec, the 1.0 of which came out last year, standardized the JSON for defining how your container is going to run. And the community has been working together on runC, which is the default implementation of the OCI runtime spec. It's the same tool that most of the higher level orchestrators are using for running containers, including Docker. So this is what your copy on write file system looks like for a container. So whenever you do like a from Fedora or from Ubuntu and then you add run instructions, at the bottom, you have layers that are shared between all the containers, and these are read-only. So that way, each container is not getting duplicate copies of the layers, and they just have their own top read-write layer. So now, moving on to why do we need different tools, and when we are wearing different hats and performing different things with containers, we need different tools, and Urvashi will go over them.
Yeah. Okay, so now that we know what containers are and what all you need to run your containers, we can break down the container toolchain into actually 4 different categories. These are 1, building your container images, 2, playing around and testing with your containers locally, 3, storing and sharing your container images, for example, moving them from your host system to a remote registry, and finally 4, running your containers in production clusters such as Kubernetes or OpenShift. And we believe that each of these categories have different security requirements. For example, you don't need as many permissions to run your containers in a production cluster as you need to build the container images. So now you can imagine what would happen if you had all these functions in one single tool. We would end up with the least common denominator when it comes to security, since production cluster doesn't need as much, but building process needs more. So when we look at the Unix philosophy, it states that you should design programs to do one thing, to do it really well, and to work well with other programs. And as you can see here, the Unix founders are pretty happy that we followed that and created a tool for each of these categories I mentioned before. These are Builda, obviously stands for building container images. Podman, it's a CLI tool you can use to test your containers locally. Scopio for storing and sharing these containers. And finally, cri-o, a container runtime interface for running these containers in a production cluster. And now we'll just go through each of these tools and what security features they have to offer for your container workloads. So the first step in your container workload is building the container image. And actually, you can see there that's the cute boss interior that Diane mentioned before that Builda has. So the first thing that comes to mind when building your container images is actually the 2 things you should keep in mind. That is, 1, how do I create secure images? And 2, how do I do the build process in a secure fashion? So for the first thing, how do I create secure images, is you want to think about minimal images. Basically, the more you have baked in your image, there's a more risk of something going wrong. You do not want to have a package manager in your image, for example. You want to do all your building and installing outside of the container on your host, and then commit the products into your container image. This way, you have exactly what you need in your container image, and you're shrinking your attack surface. And Builda lets you do that with minimal images. For the second step, how do I build these container images in a secure fashion? You can run builder inside a container, so you're isolating your build process from your host. Your build process can have elevated privileges in the container, and if it does happen to break out, it won't be able to cause any harm on your host. And actually, in OpenShift 4.0, we're going to be using builder for all the source image builds we do. And yeah, and as you would see with our other tools here, like Podman and Scopio, you can run builder without root privileges, emphasizing on please run your containers without root privileges. So yeah, we have a bunch of demos for you here. We're just going to stand here and blabber at you. So switching to demos. OK. So I started this demo before the talk, so it doesn't take a while with the internet to do the installation it needs to do. So the first thing for builder from scratch, minimal images. So builder has a command called build. Is this working right? OK. Builder has a command called builder from scratch. Is it not showing? OK. Yeah, so builder has a command called builder from scratch. And what this does, it creates an empty container. So it gives you the whole scaffolding of what you need for a container, but with zero content in it. And now you can go and add everything you need inside it. So I did the builder from scratch there, then I mount that to get the file system, and then using my host package manager DNF, I'm installing, I just want BusyBox inside this. I'm installing BusyBox in there. And that's what this whole long thing did there. And now, oh. The hard part of presentation, right? So now I'm going to unmount that container, and I'm going to commit this image. I'm going to call it minimal image, because that's what I created right here. And I'm going to use a container tool like Podman to run this image, and I'm going to try to do a ping inside it. Oh, damn, why did that fail? Right, because all I have in that image is BusyBox. Let's try Python. Yep, that fails again. So I literally just installed BusyBox in there, and that's the only thing that you'll get when you run that container image. And as you can see, that's the help menu for BusyBox. So yeah, reduce your attack surface, create minimal images. The next thing is running builder inside a container. So I've created an image called builder container, and that's what the Docker file looks like for that. It just has builder installed inside it, and has set the entry point to builder. So now I can use a container tool like Podman and run this image and actually do my build process inside it. The second Docker file is a simple Docker file I'm just showing that I'm going to build right now. And I know that command for Podman run looks pretty intimidating, but all I'm doing is bind mounting volumes in so I can access the Docker file and access the images that are built inside my container. So let's do that pretty simple build there. Yeah, and that's built. And now to prove to you that it actually built, let's list the images, and we can see my image over there. That's what I named the image I built inside the container. And from here, I can access the image I built, move it to my host system, move it to remote registries, and do all sorts of things I want to do. But I did it in a secure fashion. I isolated my build process from my host system. And that's all we have for builder. So once I create my secure image in a secure fashion, I tend to like to test it locally to make sure it has everything I need it to have and works the way it's intended to work. And for that, we have Podman. What Podman actually stands for is Pod Manager, because you can do everything from doing builds as well as running containers and pods locally. But Podman actually uses builder under the hood to do builds using Dockerfile, and tying back to our Unix philosophy, make programs do one thing and work well together. So with Podman, as I mentioned with Builder before, you can run it without root privileges. This way, admins can get away without giving access to their developers, without giving root privileges to the root access to the developers. And a really cool added advantage of this is you get compartmentalization. So multiple users can have their own containers and images on the host and won't have access to each other's. Yeah. And then the next thing is Podman takes advantage of user namespaces. So you have isolation between your host and your container, as well as between multiple containers using Podman. So if container A breaks out, a process from container A breaks out and tries to attack container B, it won't be able to because it'll be running in their own user namespace. And Podman is a true fork exec model. What this means is that all the child processes of Podman inherit the login UID of the user that invoked the Podman command. And this is very helpful when it comes to auditing, so you can look at who's trying to do what on your system to keep track. And as Dan Walsh would say, hashtag no big fat demons. We don't have a demon in Podman. Moving back to demos. So Podman is rootless. As you can see here, I do not have a sudo in front of my Podman command anymore. I'm listing the images I have that I pulled without using root for Podman. And as you can see, I have 2 images there. Now to prove to you that it's separate from the one with root, you can see that root has so many that they're in different locations. So when you're doing rootless, Podman creates all your containers and stores your images in the user's home directory. Hence, going back to the compartmentalization, every user would have their stuff in their own home directory. So yeah, and to show you that inside the container, it's root, but on the host, it's UID 1000. So that's how Podman does the rootless stuff. Basically, we're fooling Podman to think that they're running as root using UID mapping. And I'm going to show that here. So every modern Linux system has this file called etc subuid now. And as what it does, you can see your username there, and it shows the UID mapping that your username has. Right now, we're logged in as the first username, Mrunal on the system, and you can see that my mapping is 100,000 to the next 65,000 UIDs. Okay, so let's look at the directory I'm in right now, and that shows a bunch of files that I have there. And you can see the owners of those files. You can see only one of them, the third one from the top, is owned by root. Everything is owned by the user that's logged in right now. So let's do build on share. What build on share does, it takes your account and puts it in a user namespace. It does the UID mapping for you. So it maps UID 0 on the user namespace to your login UID on the host, which is 1000 right now. And then it maps, it creates a UID map for everything from 100,000, the UID map you see in cat at c sub UID, it does that mapping for you from UID 1 in the container to 100,000 on the host, and does it for the next 65,500 UIDs. So actually, let's do an ls-l over here inside my user namespace. And as you can see, all the files that were owned by Mrunal P are now owned by root inside this user namespace. And the one that was owned by root is now owned by nobody. And this happens due to the UID mapping we have. And if you want to look at what UID mapping you have, you can look at an proc self UID map. And as I mentioned before, 0 in the container is mapped to 1000 on the host and is done for 1 UID. And then 1 in the container is mapped to 100,000 on the host and done for the next 65,500 UIDs. So inside my user namespace on my container, I can create files owned by 2, 3, 4, and will respectively be owned by 100,001, 100,002, 100,003 on the host. So you're creating like an isolation between your host and your container here. So except the user namespace. But with Podman, you can actually do this for multiple containers as well. You can add extra layers of isolation between containers. And you can do that with the, oh, damn, what happened there? OK, so maybe this is not going to work. But basically, you can use the UID map flag that we have in Podman. And what I'm doing here is I'm saying, map UID 0 on the container to 100,000 on the host, and do it for the next 5,000. And if this had actually worked, you would see that inside the container would be 0 and the host would be 100,000. And then I can actually create another container with its own different mapping. So the second one I'll be creating will be 0 in the container, 200,000 on the host. And as I mentioned before, if container A tries to break out of, if a process from container A breaks out and tries to attack container B, it won't be able to because on the host, container A is 100,000 and B is 200,000, so different permissions. So there's the extra layer of isolations. And then so Podman is a true fork exec model. Well, you can see what login UID you have on the system by carrying proc self login UID, and it's 1000 right now. The login UID stays same regardless of how many times you log into the system. It's attached to what your username is. So with a true fork exec model with Podman, when I run a container and I cat that same file inside the container, you would see it's 1000 because the child process inherits the parent process login UID. Now let's try that with another container tool like Docker, which is a client-server model instead. And you will see that huge number there. Basically, that's the Docker daemon, and the user UID was never set. The login UID is not set. So yeah, that's what you have. Now let's do an audit control on etc shadow. It's a pretty important file. And now let's say I run a privilege container and I mount my host and I want to do something shady with that etc shadow file. So with Podman, once you do that and you look through the audit logs, you can actually see who tried to do that. You can see that Mrunal P there tried to do some changes to Etsy shadow file. But now if we try it with Docker, for example, and do the same thing, the UID is unset because the Docker daemon did that. You don't know who did that. So in terms of security, this is pretty cool because you can audit your system and see who's trying to do shady stuff in your system. And that was with Podman. So before I move on to the next thing, I just want to mention, some are probably wondering if I can do builds with Podman, then what's the purpose of Builder? So Podman was essentially designed for users who want to come and use our tools to be able to not have to relearn a whole tool. So you should replicate the Docker CLI, basically. And we have building with Docker files and Docker CLI. So Podman build, that's what Podman build does. It invokes builder bud, which stands for build using Docker file. But if you want to create minimal images and you want to build using a bash script and all, you have to do that in Builder. Builder is specifically designed for the build process and creating OCI images. So now we've done the first two steps. We have created a container image. We're satisfied with what it does. And now we want to share it to registries and to other people. Scopio actually stands for remote viewing and was initially designed so users can view can get like the information of a remote image without having to download it locally. So they can hit a registry and be like, I want to see what this Fedora image is and see all the tags it has, who maintains it, what the layers it has. So you can inspect remote images. It was designed in to not download random stuff off the internet, check what you're getting first, as well as the fact that people were downloading huge images and realizing this is not what they wanted and had to sit through another whole download process. We decided to take Scopio a step further and allow users to move images between environments pretty easily. So let's say you created an image locally, you pushed it to your private registry, and now you want it on your external registry, but you don't have it locally anymore. With Scopio, you can easily transfer it over without having to download it back onto your host system. So that's that. And as with emphasis on run without root, Scopio can also be run without root privileges. So more demos. This is what the Scopio command line looks like. It's a pretty simple tool to use, mainly for moving images around, inspecting them. And you can also pass in your credentials if you're using private registries. Let's do an inspect on the Fedora image that lives in the Docker registry right now. And as you can see, it's a JSON. It tells you the digest, all the repos you have there, who the maintainer is, the layers and all. So it just gives you good information of what you're about to get. And you can also inspect this and see that, oh, you want a specific tag that you didn't know, you couldn't remember the name of. So if I was like, I wanted a tag that was like Hyzen something, and then I see it's Heisenbug there. And then now after this talk, if you're convinced of sort of moving over to using Podman for your container workloads, I'm going to do a pretty quick demo on how you can copy your images over from the storage that Docker uses on your system to the storage used by all our tools. So in Docker, okay. The purpose of this was to show you the Ubuntu image in here, but it's pretty, you'll see it's there. So I'm going to use a Scopio copy command, and the Docker daemon in front just means take it from the Docker storage and move to the container storage, which is the storage all our tools use. And then, as you can see, it should be there. I can't find it. Ubuntu, right there, Ubuntu. There you go. And with the tag demo. So I was able to copy it over pretty easily. Yeah, so that's all I have for Builder, Podman, and Scopio, and Mrunal will talk to you about cri-o.
Hi, so Urvashi walked us through all these tools to build locally, and finally the most important step is you want to run these containers in production. So building all these libraries and building blocks, we asked ourselves a question: can we build a minimal runtime for Kubernetes that just satisfies the CRI using the OCI projects? And then yes, because we have runc, because we have containers image, container storage, we can build that. So cri-o started out to build the CRI using OCI, hence the name cri-o. So here's the architecture of cri-o. This is what a node looks like when you're running cri-o as your container runtime. So on the left here, you have the kubelet. Kubelet talks to cri-o via the CRI gRPC API. And CRI has two different services. There's the image service and the runtime service. The image service is responsible for pulling down images that are required by a pod. So we use the containers image library to implement the image service. And the runtime service is actually responsible for running your containers and pods. So for that, we use the storage library to create the copy on write file system. We use the OCI generate library to create a config.json that runc or any other OCI compatible runtime like Kata containers or gvisor can use. And then finally, for networking, we utilize all the nice work done by the CNI community. So any CNI compatible plugin works with cri-o. You can just plug it into the configuration. And on the top, you see a couple of pods. Let's dive into that a little bit more. So here's a view of the pod when using cri-o. So pod is the holder of the IPC network and the PID namespaces. And each pod has this infra container, which could be your PID1, so it can read the processes inside the pod. And on top of each container, you have this utility called conmon. Now, why is conmon required? So because of the way OCI defined how runc containers are created and started, we need a small monitoring agent so that we can capture the exit code of the container. And so conmon also does other duties such as writing out logs, serving attached clients, holding the TTY, reporting out-of-memory notifications from the container. So we wrote conmon in C, and the reason is because it is small enough, and since we need to run it for every container, the overall memory overhead of running conmon is very low, even for like hundreds of containers running on your node. And then finally, you have containers running with runc, but runc could be replaced by Kata or any other OCI compatible runtime. So what do you need to do to run securely in a production cluster? Secure defaults. Use read-only container file system. So your container process cannot write inside your container read-write layer. So just basically get rid of the read-write layer if possible. And like all containers and pods should be writing to the volumes that are provisioned by Kubernetes and not using the read-write layer. Secondly, use an immutable host like Red Hat CoreOS. So if a container process is able to somehow break out of the container, they are not able to make changes to your host operating system. Secondly, enable fewer capabilities. So while building and developing containers, you need more capabilities. But when running them in production, you don't need all those capabilities. So cri-o ships with fewer capabilities by default compared to like Podman or Builder or Docker or anything else you need for development. So third thing is user namespaces. So we have added support for user namespaces for cri-o. However, the Kubernetes work is still in progress, and as soon as that gets merged upstream, we'll be shipping that support. Then another small thing is PIDs limit. It's for preventing fork bombs. So one of the runc maintainers added that support to the kernel, and it's set by default in cri-o and configurable in cri-o configuration. And then last but not the least, SE Linux. So we have had a number of container breakouts over the past 2-3 years, and most of the times the answer has been, hey, if you have SE Linux enabled, then you are protected. You don't need the 0 day is not going to affect you. And this includes the latest runc CV that came out last month. So let's switch over and do some demos next. So here I have the cri-o daemon running, and I have configured Kubernetes local cluster to talk to the cri-o daemon. Yeah, so thank you. And here you can see that the node is in the ready status. And now let's try to launch a simple hello world pod. So it's running already because I pulled the image earlier. Let's try to curl it and see if we can get anything back. So it's a simple web app just that returns hello OpenShift. Now let's see what's happening underneath the hood. So here you can see that I'm using the cri-ctl tool, which can work with any CRI compatible runtime. And we can see that the my web container is running. Let's try to inspect it further and see what's happening under the hood. So here I am grepping for the conmon process, which is started for this container, and let's see how the process tree looks like. So you can see that the conmon is the parent process of the container, and then you have your actual container process. So one more thing we have done in cri-o is we integrate nicely with systemd when you use systemd as your C group manager. So you can do things like so you can use systemd tooling to watch your containers. You can see it's using 2.4 megs and it has 5 tasks in it currently. Now let's switch back and try to run another container. So we talked about read-only file systems earlier. So you can see that by default, it's read-only, and the container process cannot write anything to the inside the container. And how is this set up? We can examine the cri-o.conf, and we set the read-only to true by default. Then we talk about capabilities. So you can observe over here that I have not set cap net raw. So cap net raw allows your container process to craft any packets, and that has been the source of vulnerabilities in the past. So it's a good idea to get rid of it by default if possible. So you say, I don't have cap net raw, then how is my ping going to work? Well, there's a way. Let's see if we can get it to work. So this pod is able to ping the other pod, and how is that possible? So cri-o allows you to set syscuttles by default, and there's a kernel syscuttle which has been available that allows you to enable ping even though you don't have cap net raw. We talked about preventing fork bombs, so let's see if I can prevent a fork bomb in my container. So I'm trying to launch 60 sleep processes. And you can see that after 49 and the 50th is my own shell, I'm not able to launch processes anymore. And the reason is because I've set my PID limit to 50 by default. And here's the setting in the cri-o.conf that shows you. So basically, cri-o has all these tunables available, and we ship by secure defaults. So your containers are safer in production, and there's lesser chances of exploits affecting you. What were the mitigations for the run CCV that came out last month? Well, one was use a read-only host file system. So even if the container breaks out, it can't modify binaries on your host OS. So you should use something like Red Hat Core OS or any operating system that is immutable by default. Second is run non-privileged. So don't run your containers as root. So we saw like Uber and Splunk talk about how they had to make changes to their pods because they wouldn't run directly on OpenShift. That is, the reason is like OpenShift doesn't allow containers to run as root by default, and it locks down a lot more things by default. So it makes it a bit harder to get started, but then you are protected by default. Thirdly, user namespaces, which are coming soon in Kubernetes, will also give one more layer of protection. And finally, SE/Linux that we talked about earlier.
Okay, and so these are all the resources we have available. We have websites for cri-o, Builder, Podman. They have a bunch of blogs in them, and they link to our GitHub pages. So we're obviously always looking for contributors. If you're interested in helping out, always take a look at that. And we have a pretty cool coloring book called Container Commandos. It sort of highlights what each of these tools does in a very simple way and how they all work well together. We don't have hard copies, unfortunately, but you can go to that website and get the the e-copy. And if you're interested in playing around with the script yourself and doing it locally, the demo script lives on that link over there. So you can always pull it down. It does the whole setup and everything for you easily. So you can do that. That's it. Thanks. Oh, one more thing. I brought stickers. I'm going to put it on the table and the Red Hat table outside. So feel free to grab some.